Alrighty, so we pretty much covered almost everything when I'm talking about the basics of hypothesis testing. So here we're going to have some numbers, but in general this concept is still just the same across every single hypothesis test that we're going to see. The only thing that changes is now the final step, which is going to be our test statistics. So that one's going to be varied for each of the three, but we're going to see that from rejection region, the how to determine the null and alternate, the types of errors that we may be seeing are all still exactly the same across all hypothesis tests. So let's go ahead and look at now how to get a rejection region. So this alternative hypothesis is going to be telling you what tail you're focusing on. So if it's less than, right, we're looking at the left. You can literally say what direction the alternate is pointing by kind of the arrow. So if it's less than, it's pointing to the left, right? Greater than, it's pointing to the right. And not equal to is basically right or left. So here, again, the alternate is what's telling you what tail you're focusing on, as well as the direction of the rejection region. The rejection region basically is that tail. It's kind of like that cutoff, and from there all the way out is where we reject the null hypothesis, because that cutoff basically tells us that here's where my sample is way too far off for the null to be true. So where we reject HO. Now, the area of this little tail is given by the significance level, or alpha. So again, the alternate, if it's less than, it's pointing to the left. My rejection region is that critical value all the way down, and the area of that little tail is going to be alpha. Now the critical Z or T values, or just critical values in general, again, they separate the rejection from the non-rejection region. So these are the points where essentially, if my sample is here or any further out, that means that my null is not really kind of a good estimate for what's really happening. So again, if my null says that people weigh on average 100 pounds, and we find a sample of 100 people and the average is like 200, that's like way far off. And so that how far off it is, we basically set this cutoff and say anything further than this point is way too far off for the null to be true, so we reject it. Now, instead of using the confidence level like we did for confidence intervals, we use what's called the significance level, or again that alpha, for hypothesis testing. So why do we use that alpha? That alpha, again, remember, is the probability of committing a type 1 error, which in the grand scheme of things is worse than a type 2 error. So we're going to focus on just that for now. But yeah, power, which is again associated with a type 2, is something that you may see in future statistics courses. But just for intro, we'll focus on type 1 errors and the probabilities associated with them, or alpha. So we want really small alphas so that the areas of those rejection regions are really small, and so basically our sample has to be really, really extreme for us to go ahead and reject. And so we'll kind of see how that works in a little bit once we do some practice problems. Now, here we have the three situations that you can run into. It's either that the alternate says that it's less than, not equal to, or greater than, right? So, and that's why the null, regardless of whether your professor tells you that the null is always equal to or the null varies, the alternate's the one that really, really matters, because the alternate's the one that's telling us what direction we're focusing on. So here, on the left one, is less than 10. That's basically saying it's pointing to the left, right? So literally like pointing to the left. Does that make sense? So we're focusing just on the left tail. Now, what's the probability associated with that left tail? It's alpha, right? This is going to be my rejection region. Anything past this negative critical value, and this is 0. Now, why is it negative a critical value? The critical value is negative because, remember, with Z or T values or T scores, to the left of the means that you're dealing with negative numbers, right? So it's kind of things that we've already seen before. So here at that negative critical value, if my test statistic or my sample falls to the left of that, I'm in the rejection region, and I reject the null hypothesis. Now, the smaller the alpha is, the smaller that rejection region gets, and so therefore my sample has to be way, way far off. So basically, the further my sample is, the less of a type 1 error that I may be making. So that's why we set that alpha as always something really, really small. In general, 0.05, but sometimes even less, 0.01, 0.001. And that changes with every problem. So we'll see kind of a bunch of different examples of alphas and how the rejection region changes. But in general, these rejection regions are based off of z or t values, and we need to find that. How do we find that? So before, remember the confidence level. So I'm going to focus on maybe like this one right up here. Our confidence level was the area, this whole area here, right? From the lower limit to the upper limit, and we just did half of it to get from 0 to z, right? Because that's what our table works off of. So in this case on the left, we don't have a confidence level. We have an alpha, which is the probability of that little tail on the left. How do we get from 0 to our critical value? Basically, if this is the area that we need, it's just 0.5 minus alpha, right? Because from the mean all the way down is 0.5. That little chunk is alpha, so the difference is 0.5 minus alpha. So that's how we get a critical value for a left tail test. Now for a t focuses on, and we've seen this before, focuses on a different side. So remember, from 0 to z is how this table works. Here, the t table works off of from the t all the way down. So it kind of works off of the tail area. So in this case, z uses 0.5 minus alpha, but the t just uses alpha. Whatever the alpha is, if it's a left tail test, that's it. You just look up alpha and what? Alpha and the degrees of freedom, right? So let's go ahead and remember, degrees of freedom is just n minus 1, right? So we'll do some practice problems kind of to figure this out, but in general, that's basically the case. So now the z for a two-tail. This is considered a two-tail. Why? Because we're not only focusing on the left or the right, we're focusing on both ends, right? Is it different on either end? So this is what's called a two-tail. So what happens to our alpha? Our alpha, so we have two rejection regions, right? Our alpha then gets split into both of those. So here is alpha over 2. Here is alpha over 2. Does that make sense? So two little alpha over 2s. Now to get our z, what do we look up? Our z again needs this area here, right? So we need to find what's the probability of that area. That area is again 0.5 minus, in this case, alpha over 2. Because again, our alpha is split into two different tails. So our z is 0.5 minus alpha over 2. Now to get our t, remember, is just from t all the way up. So in this case, it's literally just alpha over 2. And what else? We need degrees of freedom, right? And then the z for a right tail test. So how do I know this is right tail? Because my little arrow is pointing to the right. So for a right tail test, this is my rejection region. What's the area of that rejection region? Alpha, right? How do we get this area? This area we need for my z, right? It's 0.5 minus alpha. And the t is just alpha. So kind of, you can generally say that, and also degrees of freedom. You can generally say that your left and right tail tests are basically the same. What's the only difference? Here, my critical value is going to be positive, right? And then here I have two of them. One on the right and one on the left. Because again, here we have two rejection regions. So if it's way lower or way higher, here it's just way higher. So we're going to have a positive one because our critical value is going to be above the mean, right? So that's about it for that. Now let's go ahead and move on to our rejection regions. So how do we write these things out? So there's three different ways, and I wrote them right underneath the way they the example that they correspond to. So the rejection region for a left tail test is that if z, which z is our z and t are our test statistics, which we'll learn how to go ahead and calculate those in the next video. And I know I'm doing this piece by piece, but I just like showing you kind of breaking down a hypothesis test, and then we're going to do full ones back to back just to kind of apply all these things at the same time. But essentially, we're going to calculate a t statistic and a z statistic. There's different formulas for them. But moral of the story is that if for a left tail test, they're less than the negative critical value that we find, and so critical values are these guys here, right? So if they're less than that critical value, then we go ahead and reject. And that's why we call that the rejection region. But mathematically, this is how you would represent the rejection regions. So if z is less than or equal to my negative z critical, you reject. My t is less than or equal to the negative t critical, you reject again. Now here, let's look at the right side. The right side is the positive version, right? So if it's not to the left of it, it's to the right of the positive critical value, we reject. To the right of the positive t value, we reject. Now here in the middle, it's kind of weird, but this is like one of the most difficult ways that some books might represent the critical value for, the rejection region for a two-tailed test. So I wanted to put it there just to explain it. What they mean by the two lines is the absolute value of my z. So regardless of what my z is, my test statistic, even if it was negative or positive, if it's bigger than my critical value, then I reject. So basically, regardless of negative or positive, just magnitude-wise, if it's bigger than either one of them, then we're going to be in the rejection region. That's generally how it is. This could break down as well into if my z is greater than my z critical or z is less than my negative z critical. That's basically what that's saying. And the same thing for the T1. Right? So let's go ahead and do a couple examples and we'll move on to practice problems so that we can kind of apply these things. So it's determined that at most 50% of people in the United States approve of Kanye and Kim's new baby name, right? So Northwest is really weird. And again, these numbers are just made up. So approximately 50% like the name. A sample of 100 randomly selected individuals revealed that 48% liked the baby's name. Using a 5% significance level, what is the rejection region? So what's the claim here? The claim is that at most 50%. And so here, am I dealing with means or proportions? So now we're doing full we have all the numbers out there. I can show you that if there's no standard deviation, you're dealing with proportions, right? So here, let's say our null and alternate. At most 50%, that means less than or equal to 0.50, right? So this is going to fall under which one, the null or the alternate? It's going to fall under the null, right? The proportion is less than or equal to 0.50, right? What would my alternate then be? That it's greater than 50, right? Now, here's what we thought it should be. We got our null and alternate, but now we actually have sample information to kind of compare it. So if our sample falls way far off from what we thought it should be, then we can reject the null hypothesis. So that's kind of how it's all coming into play. But at the end of the day, we're not doing the full hypothesis test yet. All we're going to do is now find the rejection region. So 5% significance, that's my alpha, right? And now, am I doing a right tail, left tail, or a two-tail test? So here it's looking at the right, so I'm doing a right tail test. So that means I'm going to have a rejection region here. What's the area of my rejection region? If alpha is 5%, this is 0.05, right? This is my rejection region. And now everything else is where I fail to reject, right? And so they said our null is that it should be around 50%. And these are, again, proportions, right? So sample proportions. Our null is that it should be around 50%. Again, there's going to be some variability, but let's see if it's too far off to the right for us to say that the null is wrong. So we have P is 0.50, and we're going to be dealing with Z's, right? Z because our sample is greater than 30. So remember those rules from back in the day in a sampling distribution? Z is when it's greater than 30, T is when it's less than 30. So here, we're dealing with proportions which just naturally are always greater than 30. So our Z should be 0 here, but let's go ahead and find a critical value, right? So we need to find a critical value, but in order to do that, we need this area here, right? What do we say that area always is? It's 0.5 minus the alpha, right? So here, let's get our Z critical. It's 0.5 minus alpha. Which is 0.5 minus 0.05, or 0.45, right? So once we look that up in our table, what do we get? So let's go into our table and see what's the closest thing to 0.45 that we can find. So 0.45. So we see that 0.45 is right in between these two. So what did we do when it was right in between? We just found the average of the two z-scores that it corresponded to, right? So here's 1.64. So let me scoot this up a little bit so you can see that. 1.64, right? And this corresponds to 1.65. That means we're going to use 1.645. So let's go back up to our problem. And our z is 1.645. Now, is this positive or negative? It's going to be positive, right? Because we're on the right of the mean. So here's positive 1.645. So therefore, our rejection region, if we were to write this out, it's that our z, if our test statistic is greater than or equal to 1.645. Does that make sense? So again, we haven't learned how to do a test statistic yet, but in general, if that test statistic, however we calculate it, ends up being greater than or equal to 1.645, we can reject the null hypothesis. Cool. So now let's try another example. So you feel like your 5-year college plan is is weird, so you want to see if the average amount of time spent getting a bachelor's degree is different from 5. So here, different from 5. That is not equal to 5, right? So that should fall under my null or alternate. That's going to be my alternate. And so here we have a sample of 16. So my n is less than 30. So what am I using? T, right? And we have a standard deviation. So that means we're talking about means. So mean is not equal to 5. Mean equals 5, right? And again, that comes from the claim. And so if it's not equal to, what type of test are we doing? Left, right, or two-tail? We're looking at two-tails, right? And so when we come over here, that means that our alpha of 0.01 gets split into two ways, right? So alpha is 0.01. Half goes here, and the other half goes to the other rejection region, right? And so let's go ahead and say that those are rejection regions. So what's the area associated with both of those? It's 0.005, or alpha over 2, right? And now, let's kind of piece it all together, right? So they said that our null says that it should be 5, and there should be some kind of variability around that. And so these are average amount of times that these students take in college. In Z world, that should get a 0, right? Now, again, let's find that critical value. So if this is 0.005, to get my Z, I need, oh no, actually, I'm sorry. We're doing T, right? Whoops. So we're doing T. Yeah, I should have caught that. We're doing T because the sample size is less than 30. So what do we need for T? We need the alpha, in this case alpha over 2, right? And degrees of freedom. Degrees of freedom is n minus 1. So our alpha over 2, we already know that is 0.01 over 2, or 0.005. And n minus 1 is 16 minus 1, or 15, right? So let's go to our T table. So let's go to 0.005, and degrees of freedom is 15. So 0.005, degrees of freedom is 15. So we get 2.947. So let's go back up here. 2.947. Sorry about that. So 2.947 is our critical value. Ooh, I'm about to block everything. So that means, let me go ahead and highlight this, because this is the area that we wanted, the little 0.005, when we were getting our T, right? So now we got 2.947, but we're not only on the positive end, right? Since we're doing a two-tail, we actually have a negative cutoff as well. And that negative cutoff is just the negative version, 2.947. So here, our critical T's for a two-tail is that if we get a T statistic of greater than 2.947 or less than negative 2.947, we reject. Moral of the story is that if the T that we can end up calculating is greater than or equal to where the absolute value is greater than or equal to 2.947, then we reject. And that's how we represent our rejection region in a very just mathematical format. So here we go. 1 and 2. So I'm going to go ahead and highlight these because it looks like super cluttered. So I just want to make sure it's obvious what our answer ends up being. So what do we do first? Let's do it like a step-by-step. Write your null and alternate every single time. And also write your alpha. From your alternate, you determine left, right, or two-tailed, right? Alpha then takes the area associated with that left, right, or two-tailed rejection region. And from there, we find our critical value. Whether it's Z or T, we know how to do both now, right? And now rejection region, if you had to write it in some form, this would be kind of the typical general mathematical or statsy type of way of writing these things. But in general, you can interpret these as basically when I get my statistic, which we haven't seen quite yet, and that's fine. It's just a formula. Once we get my statistic, if it's greater than 1.645, I can reject the null. Why? Because it's too far off to the right for me to say that the null is true, right? Now let's look at this one here. If my t, because we have a sample of less than 30, is greater than or equal to 2.947, and the absolute value of that t, right? So that's just the magnitude, just the number. So what that's telling me is that 2.947, whether positive or negative, if it's to the extremes of both of those, I reject. Why? Because my null says that it should be 5, but my sample is too far off for me to agree with that. Does that make sense? So we reject the null hypothesis in that case as well, if our t was greater than 2.947. So that's basically how we get rejection regions. Now let's go ahead and put it all together, right? So the next concept video, we're going to be focusing on how to put it all together and how to do a bunch of different hypothesis tests. But what I want to emphasize is that regardless of whether we're working with means, proportions, small sample, large sample, all of these steps that we've just learned are the same. The only thing that's different is the test statistic, right? So I kind of want to drive that point home. Let's go ahead and do some practice problems to get rejection regions, and then we'll move on to the different types of hypothesis tests that we're going to be working on for this set of videos.